So today I'll be talking about grammar mining. So you have already seen how to fuzz, um, and you have seen how grammars are important. So without further ado, I will start with a small recap of what you have already seen. So essentially, the basic idea of fuzzing, as you have seen, is really simple. The assumption is that no system should crash when given any input. So fuzzers try to generate inputs that can induce crashes in the system under test. Now, the only constraint in fuzzing is that we can only look for system-wide properties. So we can also look for things like memory bounds violations, safety violations, privilege escalations, etc. And you would have already noticed that fuzzing is really useful because it is automatic. That is, you can actually get off-the-shelf fuzzers and apply it to pretty much any program that you want. So it requires some human guidance, both in terms of inputs as well as checks required, but it's very much lesser than what traditional testing usually requires. So how do we generate these inputs? In traditional fuzzing, we generate random data, which is then fed into the program. And this can quickly expose vulnerabilities that the program may have, and it can lead to a crash. Unfortunately, the trouble is that when program accepts structured inputs, the effectiveness of this random fuzzing is really low, because these programs rarely return anything other than a syntax error to random input. Now the problem is that almost all random inputs are caught at what we call the parser level. And that leaves most of the important parts of the code unexplored. That is essentially the semantics of the program. So what we need to do is to use techniques that can generate inputs without this syntax error. And the principal solution, which is also the simplest solution, is to get parsers to produce inputs that conform to the expected input language of the program, or get the fuzzers to produce inputs that conform to the expected input language. So here, in this example that you see here, the input language is JSON. And if you pass in a JSON, then it is likely that you will reach the core, that is the process. So let us go for a demo now. So this is a simple parser. It's a math expression parser that parses the expressions that you are provided, and then it evaluates those expressions, providing you with an output. Okay, so this is a I will make these materials available afterwards. So what it does is that if you provide inputs like say 1 plus 1 or 2 into 3 plus 1 or 1 minus 2, etc., then it actually evaluates, it parses this first, and then it evaluates these inputs and returns you the result. Now what we want to do is to figure out whether you can actually reach the internals of the program. That is, does the parser result in a valid input if you produce a fuzzer? And here is our random fuzzer. Okay, this is a random fuzzer that generates inputs randomly, and we produce a total of 10,000 inputs and try to generate inputs that passes through the parser. And if it passes through the parser, then we know that it has entered the core. So let us try producing these inputs. How many of these inputs would actually be valid? So here we are trying to generate it. And here you can see that we have generated inputs, of which less than 1% is actually valid. That is, random generation is really bad when it comes to parsers. And you can see that the actual variety of inputs is also really bad. So what we need is actually the grammar, so that we can generate good inputs. So when we say that we actually want the grammar, it means that the inputs should be able to conform to a particular specification. This specification is called the grammar. And here is a JSON grammar, which is a context-free grammar. And context-free grammars, as you might already know, is just like procedure definitions in programming languages. We have a number of keys and associated definitions for it. And each definition contains multiple expansion rules, and each expansion rule defines one way to expand the non-terminal and contains terminals and non-terminal symbols. And each non-terminal symbol in turn has their own definitions. And the terminal symbols like true, false, and null, they are simply basic alphabets of the input. Now, these grammars represent the input language that any input can be represented as a sequence of application of the rules of the grammar. And we call this particular construction the derivation tree or the parse tree. And the more important idea is that once you have such a grammar, then writing a grammar fuzzer is really, really simple. Here, this is a simple grammar fuzzer in about 15 lines of Python. And the interesting thing is that you can customize these fuzzers to any extent that you want. And you can fuzz your programs. And another thing is that once we have these grammars, you can also write parsers. If you have already been through the software engineering compiler course, you would think of parsers as really complex piece. But a parser is simply a grammar fuzzer that is turned inside out. And here is a complete parser that can use this JSON grammar to actually parse JSON inputs. Now, why do we need a parser when we are fuzzing? The interesting part is that once we have the grammar, once we have the fuzzer as well as the parser, then you can actually take existing seed inputs and then you can actually combine features from these different seed inputs, producing inputs that that can reach deep into the program logic. So here is a lang fuzzer. This is essentially a fuzzer that can make use of seed inputs and produce valid inputs containing these features. And as you can see, this is also less than 20 lines. And all these things are very, very simple to use. Now, given that we can produce such interesting fuzzers using grammars, where exactly do we get these grammars from? Because as developers, we rarely start anything by defining the specification. Even though professors always tell us to start with specification, no one ever does that. Almost all of us actually try, trial and error and see, write handwritten parsers to produce programs that consume inputs. So we may not actually have the input specification. That's the grammar. So what do we do? And there are a number of solutions that exist. So these can be divided into black box induction and white box grammar induction. This is just to show you that there exists a lot of research in this field, and I won't be going further into the black box grammar induction. I will be simply focusing on the white box grammar induction, especially the string inclusion technique, which is present in the fuzzing book. So we start with string inclusion. So this is something that you already have seen in the fuzzing book. And here is our chapter on mining input grammars. So here we have a grammar challenge. So we have a small input processor that is called a process vehicle that takes inputs from a user and then tries to process the input in a particular way. And it is essentially a CSV file which contains some additional constraints. So this is a process vehicle that takes in a particular vehicle as a string, and then it splits that particular string based on commas. And if it is a van, then it returns process van. Otherwise, if it is a car, then it returns a process car. And if it is a process van, then you have a particular result string that says that we have a particular van of a particular vintage. And if the year is greater than 2010, then we say that this is a recent model. If not, we say it's an old model. Similarly, we have process card. Now we want to produce inputs for this. How do we do this? So as you saw earlier, producing inputs that conform to specification is really hard when you use pure random fuzzing. So here is a solution that you have. So we start with importing the book utils. So this is the fuzzing book, and we continue with most of the prerequisites, and we have a few selected inputs. So these are our inventory that the user will provide. And the idea is that we want to produce the actual grammar for the process inventory. So here we have run this, and then we start with a simple grammar miner. First, we split our inputs into a few arrays, and we also have a list of methods that we want to extract the grammar from. And you have already seen how to write simple tracers for fuzzer, for coverage. So we do the exact same thing. So we have coverage, we import the coverage, and we have the tracer. And once we have the tracer, we can run our process vehicle under the tracer. So this is essentially the same technique that we use for string inclusion. The essential idea is that we want to capture the inputs that are present at each subroutine calls. So let us go back to our grammar, our demo. So what string inclusion does, okay, this is URL parser. This is not the process inventory, but here, so URL parser is essentially another function that parses URLs, and this is an example that I am using. So what it does is that we want to hook into each of these subroutine calls, and we want to identify how the input, so here the URL is decomposed by the parameters to the function. So here the parameters to the function are URL, and then we also want to see how this parameter is decomposed into local variables. Now the idea is that how the variables decompose the input actually provides us with some idea of how the input is parsed, how the parsed tree looks like. So let us see how that happens. So here we start with our URL, sorry. So we start with our URL, that is http:// at www.google.com:80, and we have a query string as well as a reference string. And as you can see here, when it is assigned to URL, we have URL which contains this particular string, and that means that we can actually start replacing the first string, the first parameter, by the URL. Okay, and next we have this scheme that is assigned some value from the course arguments. So scheme contains HTTP, which means that we look for the previous variables that are present that already contains this substring. So the idea is that if the substring is present in a previous variable, then we can replace that particular substring in that variable with a reference to the new variable. So here we can replace the HTTP in the URL with a reference to scheme. Next we go for netlog. So netlog is the result of scheme netlog URL query. This is the result of split result. And given that we have user pass at www.google.com, we can replace the corresponding string in the URL, which is the only string that contains this netlog, with a reference to netlog. So this is what we do. Then the next one is query. So q is equal to path, and again that is present in the URL. So we replace that particular substring with a reference to query, and finally we have the fragment, and the fragment is again ref, and we replace that with ref. So this is essentially what we want to do. We want to hook into the subroutine call, and then as and when each of the individual variables are assigned values, we want to look up in the parameter or the previous assigned variables and see whether a substring, the particular string that is assigned to this variable, can be seen as a substring of the previously assigned variables. If it can be, then we replace that particular substring with a reference to the current variable. And by doing that, what we get is actually the decomposition of the input. So start is decomposed into URL, and URL is decomposed into scheme, netlog, query, fragment. And of course, scheme is HTTP, netlog is user pass, query is queue_path, and ref. And we do that for different inputs. So here is another input, that is HTTP sysbar.sarlen:18. And here is another input, again the same method, and we have fuzzing.org, which contains a reference. And this is our tree, that the parse tree that we generated by following this particular procedure. And once we have that, what we do is to simply combine all these trees. And how do we combine that? We look at the particular start point. So start is our start symbol, and that is present in all the trees. So we start, we produce a definition, a grammar, which contains the definition URL, because URL is the only child of that particular tree. So we produce a tree, produce a grammar which has the definition of start containing the only expansion, that is URL. Now what about URL? If you look at the tree here, URL is expanded into scheme : //netlog, query, sharp, fragment. And here the other one, the second input that we produced, URL contained with scheme : / and netlog. And the third one only contained scheme : / netlog and a fragment. So we simply use all these expansions, the first level expansions, as the definition for the URL here. So the top one is the expansion for the first tree. The middle one is the expansion that we get from the second tree. And the third one is the expansion that we get from the third tree. So this is the definition of the URL. And then we look at each of the the names that we define here: scheme, netlog, query, and fragment. These non-terminals we in turn look up in each of the trees. So in the first tree we have scheme is HTTP. Second tree we have the scheme as HTTPS, and the third one is HTTP. So we again define the scheme as HTTP or HTTPS. And we go back here and look at the next one, that is netlog. And here netlog is either user:password google.com, or netlog can be sysbar.sarlen:18, or it can be the fuzzing.org. So we simply define the three different alternatives for netlog. Query contains only one particular expansion, that is queue_path, and fragment contains two expansions. It can be either ref or it can be news. So this way we can simply collapse all the trees that we produced until now into a single grammar that combines all these trees, and this gives us our grammar. So let us go back and see how that works in the demo. So we first produce a context, which all these things are done for capturing the input from the subroutines, the parameters of the subroutines. So we have the context, and we have a log event, and then we use a tracer for hooking into the subroutine. Now we have a tracer that can hook into the subroutine and then log each of the parameters and the variables that are declared. And we run our process vehicle under that tracer. And we see that we have a number of traces. Okay, so we produce the tracer. Okay, these are all tracings that you can look up in the book. And once we have our tracer, we run it with the first vehicle input. So let us see how that works. We have the first one, and then we look at what traces were involved. So we have process vehicle, which was called with a vehicle 1997 van Ford, and process vehicle that was in we captured another variable assignment here. in the line process vehicle, and then other variable assignments then that came into the van with these values. So the parameters were year 1997, company was Ford, and model was E350, and then we had different variable assignments. And then at the end we had a return from process van and then return from process vehicle. So these were the parameters and the variables that we captured from calling process vehicle. And then we try to extract the assignments from these defined variables. So from each of the assignment, now we want to extract the substrings that are common. So we define a substring as at least 3 characters in width, and we will see why that is required. The idea is that we look for variables that are at least 3 characters wide, and then try and see previously defined variables or parameters that contains this substring, and that is what we do here. And we do that. We try figuring out the fragments, and then at the end we try to extract assignments that we have from our defined tracker. And here the assignment was variable, the vehicle, and again the vehicle was assigned 1997 van Ford, and year was assigned 1997, kind was van, company was Ford, and model was E350. And here is our parser, and if you see, this is what we extracted so far. So we extracted the vehicle as the parameter. That is what we got here. And by hooking into the subroutine, we extracted the variables, the year, kind, company, and model using the defined tracker. So we have that. And from that, we want to now extract the derivation tree, as I mentioned. So we have the derivation tree, and here is how we define extract. Okay, these are all examples, so let me go through that fast until I reach the main point. And here is our miner, the tree miner that tries to extract the grammar. So first we extract the derivation tree. This is the definitions for derivation tree. These are all things that you can look up, and here we see how the derivation tree looks like. So here you can see that we start with a start, and that contained the input string that we produced, van, Ford, and E350. We have definitions. Okay. Here we attach the tracer to the tree, and we have our derivation tree that extracts the derivation tree from the input. So we produce an input, and then we ran our input under the tracer, and from that we produce the derivation tree. And as you can see, this is the derivation tree. Start contains the non-terminal vehicle, and the non-terminal vehicle is in turn containing year, kind, company, and model. So here is how we combine everything together for each of the different inputs that we have. And from here, we now look at recovering the grammars. So this is again what I have explained. We simply collapse the trees to recover the grammar. And as you can see, we have a grammar here. So we have start, which can be expanded into vehicle, and vehicle can be expanded into year, kind, company, and model, and year can be 1997, kind can be van, company can be Ford, and model can be E350. So let us produce the syntax diagram for that, and now let us run the entire thing once with the entire set of inputs that we have. And as you can see, we have different years and different kinds because we had multiple inventories. So this is essentially the basic idea of string inclusion. So again, what we have done is to collect a set of series of example inputs, pass these inputs through the subroutine that parses this input, hook into the subroutine so that we can figure out which are the arguments, which are the local variables, and then figure out the decomposition of these local variables that corresponds to the specific substring of previously defined parameters or variables. So now let us go back.
Rahul, I think we have a question in the chat. I'm not sure if you can read them.
Okay, we have. Yes. So can you possibly, oh no, that was a different one. What happens if there are multiple matches? For example, the scheme HTTP would match twice in www.http.com. That's a really perfect question. And if you will wait for 1 more minute, that's exactly what I'm going to talk about. Thank you for the great question. And that is 121. Who would be 121? Anyway, so let us go back to our presentation. So we got the tree and we got the grammar. And if you read the fuzzing book, you can see that this can be expanded into places where there are different variables that has the same name. How do you deal with that? What happens when different functions are present which reuses variables? All these things are explained in the fuzzing book. Now the main question here is this. So let me go with this. So this is the question that you asked. What happens when there are multiple subroutines, substrings? That is, HTTP may be present elsewhere, and user colon password can also be present elsewhere. So each of these things can be present elsewhere. So the string inclusion technique, by what we have actually provided so far in fuzzing book, doesn't actually let you do that, because you are completely reliant on looking for substrings. Now there are 2 ways that you can actually overcome this. One is a research topic that one of my master students has just defended his thesis. The other one was done by a different PhD student called Matthias, who published a paper called Autogram. And the idea is that rather than looking for string inclusion, you look for something called information flow. That is, you try to figure out where each particular character in the input string is processed. So you attach a particular something called a taint, and this is again present in the fuzzing book. So let me actually say the chapter name. So if you are more interested, you can look up in this particular chapter called tracking information flow. And this is essentially the technique that we use. The idea is that you attach a particular taint or different taints to each of the individual index input characters. So you have a taint of 1 to the first character, taint of 2 to the second character, and so on and so forth. And when you extract a substring, then you actually get a tainted substring back, which precisely tells you which part of the input it actually came from. So if you have user colon pass here, so if you extract the scheme HTTP, it will precisely tell you that it came from the initial HTTP and not from the final HTTP. And this is made possible by tracking the information flow. And this is actually implemented in Autogram. And it is also implemented as an exercise in the fuzzing book that you can look up. Another issue that we have is low accuracy. The trouble, it is very similar to a duplicate string. The issue is that I already mentioned that we were looking for 3-character long strings. Why is that? The trouble is that if you go any lower than that, for example, if you go for single character strings, then the duplication issue becomes even more worse, because there are only 26 characters in the English alphabet. So your decomposition becomes extremely difficult because there could be multiple duplicate strings. In which case, one way to do that is to essentially discard any inputs that contains duplicate strings, which is not going to scale very well. Or you can go for this information flow tracking. The third idea is called MIMID, which I will be taking, which I will be discussing right now. So let us go for that. So I talked about autogram, and then I mentioned why autogram can be implemented using information flow. But there is another issue with autogram. The problem is that not all parsers that we have are actually written in the particular format that we expect. That is, not all of them are written in a procedural decomposition way. For example, this is a standard way of writing parsers in Python, or rather the newly recommended way of writing parsers in Python. And this is called PyParsing, and this is a combinatorial parsing style parser. And you can actually see that this is a very different way of writing a parser. That is, we define inputs, we define individual elements of the parser without using procedures. These are simply defined as variables, each of which parses a particular part of the program, a part of the input. And at the end, you simply parse it by using. My system has become very slow for some reason. So yeah, you can simply parse it by calling a particular method called parse. And this is essentially a different way of writing parsers. And the trouble here is that we don't really have the string decomposition, or decomposition from parameters to local variables that we were reliant on previously. And there are, here is another one. This is essentially how JSON is defined using PySec, which is again another combinatorial parser. So we define JSON as a choice, and you have a number of characters. So these are things that you can look up later. But the idea is that not all parsers are written in the way that we expect. And the trouble is that if you have such kind of parsers, then the grammar that we get is really, really bad. Now, what do you do when you have such things? This is where I have been working in the last 2 years. The idea is something called conversion of a structured control flow to grammar, and this is called Mimit. The basic idea is essentially this, that if you have a program, then you can extract the control flow of the program. So what is a control flow? Control flow is essentially the flow chart of the program in question. So you can actually, if you have a program, it would contain, say, if conditions, loops. So the first one is a sequence of statements. That is a statement for A followed by B followed by C. The second one is an if condition that contains a true branch and a false branch. And the third one is a loop that essentially loops, defines an iteration. Any conditional or any loop can be expressed, or any program that is written in a structured format can be expressed as a combination of these elements. And the idea is that such control flow can be translated into a grammar of the control flow, a direct translation. And from here, we actually extract the grammar. Now, how do we do that? The idea is essentially to start with something called a control dependence graph. And a control dependence graph is essentially a graphical representation of the program where each statement gets a node. And there is a directed arrow between control dependent nodes. So here, statement B is control dependent on statement A if A determines if B executes. So here, while determines whether if is executed or not, because you can actually skip the if condition completely. And once you have that, then you extract the dynamic control dependence tree, which is essentially a way of extracting the execution paths through the program. Essentially, each executed statement in the program is a node in the tree, and each execution statement is control dependent on the statement that caused it to execute. Before I go further into this, let me mention that this is not present in the Fuzzing book. This is current research. You are not expected to understand this. You are only expected to understand how to use the Fuzzing book grammar miner so that you can recover your own grammar. So this is more research. So once you have these trees, then you can attach the input characters to these trees. So here our input was 1, 2, comma, and this is parse CSV, and we passed it 1, 2, and we can attach the individual characters to the leaf nodes of the tree. And this gives us the parse tree. And once we have the parse tree, then we can actually essentially go through the parse tree and then identify which nodes are compatible. So essentially which nodes can be collapsed into the grammar, and you can extract it by using a lot of iterations. So I will not go further into this. For those who are interested, you can look up our paper on Mimid. Okay, and this can be collapsed into a grammar. And this Mimid actually gives you a fairly accurate grammar of pretty much any kind of recursive descent parser that you want. And using this grammar, you can extract, you can fuzz your programs, and that comes, and we have time for a demo. So let us go for a demo. So here is our the implementation is present in something called PyMimid, and that is present in GitHub. So you can look up PyMimid, which is the repository which contains this implementation. And here is our subject. So let us look at calc. So here is a simple calculator, and the way you do it is make readable calc. And this is the grammar that you obtain. So here is how it extracts the grammar. And this is the grammar that you obtain by running Mimid on the calculator parser. There are other subjects. So here is another one, math expression. And this was the expression parser that we discussed earlier. And as you can see, we again derive a fairly detailed grammar. So start contains main contains get value contains parse expression contains parse addition, multiplication, and parenthesis. So let's look at math expression, and math expression has. So get value is what we call. Get value contains parse expression contains parse addition, which contains parse multiplication, etc., etc. And this is essentially the same grammar that we get here. Okay. So this is the grammar that we got that almost exactly represents our program that we discussed right now. Okay. So now this is the paper. So the whole research is described in this paper called Mining Input Grammars from Dynamic Control Flow. And you can look up if you have any further questions, or you can actually ask me if you're interested in grammar mining. Now, there is one more part that we are missing here, which is that for Mimid or even autogram or string inclusion to work, you need what is called reasonable inputs that exercise all features of the program. Essentially, you can only mine parts of the grammar where you can actually track the execution. Without tracking the execution, you are essentially blind to that. So how do we generate these inputs? Unfortunately, this is a very hard problem. Thankfully, there are various ways in which you can actually achieve fair coverage of the input. So here is another mechanism that we have for generating inputs. The essential trouble that we have is that what we want grammars for is to generate these inputs to the programs. But if you already have these inputs, then that is what you wanted. You need these inputs to mine grammars, but it is for generating these inputs that you wanted grammars in the first place. So you have to break this cycle somehow. And what I discuss next is the way to break the cycle. So the essential idea is that you want to write your parser in such a way that it can distinguish between incomplete and incorrect inputs. The idea is that if the parser can actually tell you that some input is incomplete or incorrect, then you can repeatedly query the parser for larger and larger prefixes. So here is what we do. So we start with an empty string and then ask the parser whether this empty string is complete or is valid or not. And the parser tells you that this is incomplete. So what you do is that you add one more character to the input string and ask the parser again. And the parser tells you that it is incorrect. But when it actually tells you that it is incorrect, you can actually look at what can actually make it incomplete. So for example, here you can actually see that if you add a parenthesis, open parenthesis to it, then the parser will essentially tell you that, okay, now the second character is incomplete. So the input is now incomplete with 2 characters. And then you can attach one more character and ask the parser again. And as you add more and more characters to the input, the parser will tell you that this is incorrect or incomplete, and you can either replace the current character or add more and more characters to the input. And at the end, this gives you a complete string, and you can do this again and again and again, getting you larger and larger inputs. So this is essentially the way that you can generate inputs for mining these input grammars. And here is a demo for that. So here is a micro-JSON parser. Micro-JSON is essentially a smallish implementation of the JSON parser, and what it does is that it accepts a particular input, and then for each input it will check whether it's a valid JSON string or not. And if the JSON string is valid, then it returns that the string is valid. If the string is not valid, then it will check whether it is a prefix, it's a valid prefix or not. And if it is a valid prefix, then it will tell you that this is a valid prefix that is incomplete. Otherwise, it will tell you that this is incorrect. So this follows the particular specification that we described earlier. So what happens when you run the particular generator that we described? So this is how you run it. So this is essentially appending each and every character to it, and you can see that this has already figured out that this is starting with a quote, and then it generated inputs, and it generated a complete quote. Now it generated a number. Let us run it again once again to see whether it can produce better results. Yeah, so it has produced an array here, and it is trying to append more and more elements to the array. So it produced one element to the array, and it produced an empty string. Here is another. Yeah. So this is essentially how you can produce larger and larger inputs using the directed generator, and you can produce inputs that cover all features of the program simply by executing it again and again. So as you can see, it produced an array with a first number and then a quoted string. Yeah. Okay. And it has produced another array, and so on. So this will go further. So let's go back. So that ends my talk. So we have described why the grammars are important, and we have described how the grammars can be extracted using the string inclusion technique, and the current research that is essentially about extracting the grammar from the control flow. And finally, I have also discussed how you can generate these inputs that are required for extracting grammars without actually using the grammars in the first place. Thank you for listening. Let me know what questions you have.